All right, welcome everyone. Welcome to our MPCR speaker series that we're kicking off this semester. My name is William Hahn, and I'm very happy today to share you some of the ideas I've been thinking about in terms of natural and artificial patterns. So let me just jump in, and we'll be taking questions in the comments. So that if anybody's on live stream, put them in the comments, and if we can't get to them live, we'll follow up with you after. So I want to talk about life, I want to talk about biology, and I want to talk about AI in the context of patterns, both recognizing patterns and generating patterns. And so we can think about our entire life as a sort of pattern, our biological pattern, our mental pattern in our mind, and then the patterns we see in culture and even in the universe at large. We're going to try to think later in the talk about how we can find patterns throughout the universe. So what do patterns in nature look like? If we were to go out and capture with a camera or take some observations, we might expect to see things like this. But strangely enough, this is not a real pattern. This is an artificial pattern. And we're now approaching the era of passing what was called the visual Turing test, where as humans, we can no longer easily distinguish between natural and artificial patterns. So I want to think today about agents, about life, about little critters that have a goal of just being alive. And how do they operate? And how could we take understanding from these systems and bring it to the technological systems that we're building in our economy today? We can model ants as virtual life forms in a computer program. And this simulation style started back in the mid-'80s. And now we have the ability to scale this up to millions of little agents in the simulation, and maybe more importantly, give them intelligence. Each one of these little critters in these agent-based models could have the potential capability that we see in things like ChatGPT and other large language models. The point being is if we scale out to a certain viewpoint, we look just like those systems. And we have a lot of situations on our planet, problems, let's say, that we're trying to figure out. And can we reverse engineer and take solutions from those world of ants or from the world of artificial ants and try to understand our social problems? So a lot of this lives in an area called natural computing, which is really at the overlap and intersection of a lot of classical branches of science. And when we try to understand things like murmuration and these large flocking patterns, it's not clear if we should use the regular tools from physics or from chemistry, or if we need something different, a complex systems approach, where we try to model how these little agents, we can call them, are interacting with each other. So if we look at this breakdown of natural computing, there's a lot of things that we study here in the lab. And so we can see things like swarm intelligence, or now one of the most powerful technologies on the planet driving large language models, artificial neural networks. And you can see these fall underneath bio-inspired computing. But there's a couple other ways to think about it. One is trying to figure out how nature itself is acting kind of like a computer. Not like an Intel chip or an NVIDIA GPU, but it does things in a very different way, but it does something like computation. And then what we're going to talk about mostly today is this idea of artificial life, where we're going to simulate natural phenomenon in computers. And I would argue that those simulations are getting very realistic in terms of the capabilities of the agents and very practical in terms of our economy. So like artificial intelligence, this field is not new. There's some great work going back to the 80s and 90s in this field called artificial life, which is kind of like the little cousin of AI. And I would argue in a sense it might be in the long run even more important because these critters are going to inhabit our world. They're not just going to be browser tabs or apps on our phone. They're going to sort of have their own reality in a sense. This is an early simulation of flocking like we saw. This is called the Boyd's model, right? I think Nancy updated my slides there. And that was a simulation of bird flocking. But we can do that for things that move or things that don't move. And so here is a variety of artificial plants, trees that are generated by fractal algorithms that look strikingly like real trees. And what's amazing is we can now set up this digital forest, and we can have them evolutionary pressure, like select which one of these are going to survive the next season. And now we can actually let these artificial creatures evolve. And we can give them goals like who can get the best canopy coverage, or what makes the best habitat for squirrels that might inhabit them. But if we add this idea of a selection pressure and choose which ones pass their acorns on, and we have mutation, then we can get this idea of emergence, where we really do have something like the primordial ooze in the early ocean, where life is kind of bubbling out, but in this case of our computer chips. We still don't understand how these systems work. We can't build AI that are anywhere near as efficient as systems like this. Seagulls run on sardines. And now the AI industry is building computers the size of Manhattan, and the power bill to match that. We need to take inspiration from these systems to figure out how we can run on ocean water and small fish, things that are quite sustainable. We need to look at the organization of eusocial species like bees and termites to try to figure out how are they organizing their society? How are they getting rid of their waste products? How are they creating sustainable building materials? How are they making architectures that scale way beyond the understanding of any ant? And these are the things that we need now in our society. Here's a really interesting ant termite simulation, just like the one that we saw with the ants. And what's really amazing is you can have an incredibly dumb algorithm on these little virtual ants. And in this case, what they'll do is they're going to sort out these little tiles. And so if an ant is not carrying anything, it will walk randomly until it bumps into a particular tile. And if it's not holding anything, it'll pick up that tile and it will carry it around until it reaches another tile of the same color. And if it bumps into a tile of the same color as the one it's holding, it will just let go of one it has. It's as simple as that. It doesn't really have any goal. It doesn't have any understanding of what it's doing. But that simple recipe, if we let it run, the ants will sort out all of the different tiles into piles without really knowing that's what they're doing. The recipe doesn't say sort tiles. It just says carry a color if you're not carrying one, and drop it if you bump into the same color. I imagine in maybe 10 to 25 years or so, we'll be able to drop very small robots like this onto a landfill and say, please pile all the aluminum over here, and all of the silver over there, and all of the gold and platinum over here. And we won't necessarily have to have a very sophisticated AI inside each little robot. They could be doing a very simple heuristic like they do in nature here, which ends up building some really tall structures. It's interesting that for millennia, these were the largest structures on the planet. You know, humans, it took a long time before humans could make something that was more impressive than the termite mounds. I'm a big fan of sort of going back to the future. And in the 80s, there was these amazing titles that kind of went under the idea of game, but they also had this simulation in the name. And in this case, simulating life or simulating the entire planet. And I think we need to get back to this approach, and we can beef this up with, one, higher resolution graphics, but also the massive compute capability that we see in graphics cards now. We have incredible memories. When we buy a laptop now, it's going to have gigabytes or terabytes of disk space and memory. And so that allows us to take these simulations and really scale them up. But these were pretty sophisticated at the time. And it was this idea of a digital organism, which is very related to artificial life. And you create something that has a metabolism, maybe it has goals, maybe it interacts with other organisms in the ecosystem. This was the sim life, and you could sort of swap out the roots and the bulbs and things, and you could get different sort of versions of these life forms, and to see how well they were adapted to the environment that you dropped them in. Amazingly, back in the 1950s, Edward Moore started to think about this in a very practical, grounded way. He said, can we have factories that reproduce themselves? Kind of like a 3D printer that makes 3D printers, decades before that idea was around. And they were kind of like little fish. And then here you can see they're called little lemmings. And it says, like lemmings, a school of artificial living plants. And here he's being cheeky. He means plant like as in an oak tree, but he also means plant as in like a factory where you build stuff. And so these artificial living plants swim into this harvesting factory, right? So they go home automatically, and then you can collect the pieces. And what each of one of these will do is this will go out and anchor itself on a riverbed. Here you can see our model, which is the seagulls and the ocean shore. And this is a sort of a Dr. Seuss style conception of what it might look like, at least from the viewpoint of the 1950s, to have an artificial living plant, in this case modeled after the squid. When securely moored, it will begin the process of reproduction. Right? So this is really a very early idea of artificial life, but in the sense that it will do things and harvest raw materials from the world for us. Well, Florida is already full of these little critters, right? You have them in your kitchen, you have them in your yard, and they are very good at running around and collecting resources, and they have a kind of intelligence that's emergent and distributed. And I think that's what we should expect to see out of the AI. Not every little chip has to be a super intelligence, but when they work together, really interesting stuff will start to happen. So I want to look at how we can find these kinds of patterns that nature leaves, look at its fingerprints, and then reverse engineer it to abstract forms that we can use in technology. And so this is a olive shell, and you can see it has this amazing pattern, which is strikingly similar to this Sierpinski fractal. And we can create simulations of this. This is a real olive shell, and this is a virtual olive shell. And we can try to figure out what is the computer program, let's call it, that biology is executing or unfolding that ends up giving that pattern to the seashell. Now, the seashell's a really good example of patterns, but our brain folds have patterns, right? Our fingerprints have patterns, our iris and retinas have patterns. And so that's what we try to want to figure out, is how biology is capturing and using these patterns. So there's an area called cellular automata, which was largely developed by Stephen Wolfram and John von Neumann before that. And it's kind of a digital physics. It's sort of a graph paper world where we try to figure out what patterns could exist in a very simple universe. And there's an amazing sort of encyclopedic overview of all of this that you can take a look at. It's called A New Kind of Science. We have a copy of it right here in the lab. And it's trying to figure out, how does nature produce patterns? And by following these very simple recipes, we get out rich structures. And so it's kind of like starting with just a very simple ingredient, like say just a bag of flour, and then suddenly you have a 4-layer chocolate cake come out of it. It doesn't seem like it was in the ingredients. And what Stephen Wolfram was able to show is that a very simple recipe, here you can see the entire program is only 8 bits. And what we do is to figure out what the square is going to be, we look at the previous line, and we look at the neighbors, and we find the matching pattern here. And then we choose the one down there. This square will tell us what the update rule. It will tell us how this thing is going to change over time. And it's a very, very simple recipe. In a sense, you cannot make a simpler computer program. 8 bits is hardly enough to even write the name of your computer program. But here we can see it creates something. I think of this as like rain on a car window. It looks very natural for something that the program doesn't seem like it would warrant that sort of complexity. What's interesting, Alan Turing, who essentially developed the modern computer as we know it conceptually, the later part of his life, he was fascinated with animal markings and this idea of morphogenesis and trying to use computer programs to figure out how these kind of patterns in nature emerge. Because if you're the stripe on this tail, you have to figure out if you're going to be a dark stripe or a light stripe. But every cell has the exact same code. All cells have the exact same DNA instruction set. And so how does a particular cell, whether it's on your hand, know to shoot out a hair follicle or to skip it and let your neighbor do that? And that is all over us, from the top of our head to our toes and everything else in between. And so we want to try to systematically explore the patterns that we see in nature, and then can we reverse engineer those to try to figure out how we can mathematically instantiate those. So these are some of the patterns that we're developing here in the lab. This is a generalization of the Wolfram automata to use the techniques from neural networks. And we can create a large variety, essentially an infinite number, of these very simple little petri dish worlds And then we go through and think almost like a hadron collider or an atom smasher. And what things show up? If we let this thing run over and over again, can we get interesting critters? Kind of like if we were to take a petri dish and swab all over things and then let it incubate. What happens to that system if we let it run? And so these are essentially digital petri dishes where we can run these virtual worlds and see what emerges. I really like this quote by Immanuel Kant, and he said, "We will never have an Isaac Newton for the blade of grass." And what he meant was things like the moon and the stars, we can write down formulas. But biology, cells and plants and chlorophyll and sunlight, this was forever beyond humanity, was the idea. And I would argue that that's not the case anymore. We are closing in on this. And I think there's some extraordinary work being done that will take the biology that we have in the world and ground it in the same kind of way that we have in physics. And this will lead to breakthroughs in medicine and longevity and just understanding our places. So fractals was the other little piece up there next to artificial life. And they're intimately related because we can use all the variety of forms that come from these fractal algorithms and then try to think, okay, is this what nature is tapping into? We traditionally thought that evolution had to find and create and engineer all of these delicate patterns. But it seems more now that these are already out there, that nature is already making use of all of these weird patterns, and that as living systems, our DNA can just kind of find them and make use of them. It can recycle them. We used to think that biology or the world looked like clockwork. We thought we could just make sort of fancy, sophisticated watches, and then that would scale up to robots. We now know that's not the case. We need a different approach. We can't just have a 3D printer print a smaller printer, which prints a smaller printer, which prints a smaller printer, because eventually the stuff sort of stops. You run into a different physics, which is the same, thankfully, the same reason you don't have giant mosquitoes, right, or tiny elephants. There's a scale in which biology operates, and we have to learn those scaling laws. This is one of my favorite critters that I've come across recently, and I call this a mathematical fish. And what's interesting is it's not a computer animation in the traditional sense. It's not even a computer program in the regular sense. That's a formula. It's a mathematical formula like sine wave. And here we're just simply animating that. And here's another version of this. It's kind of a more generalized version of what's called the game of life. And we can make these little critters. We can find these little spontaneous kind of digital fish that show up in these mathematical spaces. Now, it's very different than if we make a video game, say like a Grand Theft Auto. We would get simulate a model of a car. We would say, here's the car on the street. And then we would tell the computer to animate that car going down the street. This isn't of that type. This is more like a sine wave, and you say, we want to plot that. So we'll see some more of those in a minute. And the idea is that when we look at these little weird critters, right, these aren't made out of the classic shapes that the Greeks gave us. They're fuzzier. They're stranger than that. This is where we need these fractals. So Benoit Mandelbrot, he suggested that when we look at nature, we shouldn't expect to see triangles and squares. They're not out there. In some sense, they're nowhere. There's all of these other things. There's ferns, there's honeycombs, there's wisps of smoke. And so when we try to understand our form, right, those are physical form, but even the patterns in our mind, we have to start thinking in terms of these other shapes. So here's some simple versions of these fractals. This is kind of like digital wheat or something like that. And you have a very simple recipe. And the recipe says, every time you find a straight line, replace it with 3. And so then you go to the next one, you replace that with 3, and the next one, you replace that, and so on. And you get these branching patterns. And so when we think of plants evolving to survive the winter or to have big wheat because we're harvesting them, what they're tweaking is these very simple recipes. Nature doesn't have to solve the whole thing. It has to do it like the ants and the tiles and figure out this very simple heuristic and then just run that. And the complexity will just emerge from nature. So this is one of these ferns. This is called the Barnsley fern. And again, what's really striking about this is not a computer program. This is a mathematical equation. And when you find the solution to that equation, this happens to be the result. And so I suspect that that's kind of what nature is sampling when we find these forms out in the wild. This is a new version of artificial life called particle life. And it's striking how simple this one is in its rules. And so it's kind of like a generalization of gravity. In gravity, everything gets pulled to everything else. But here we have different colors for gravity. And so we can say that red is pulled towards blue, but blue pushes away from purple. And purple gets pulled towards yellow, but yellow gets pushed away from green. And so we can set up very simple rules, again, kind of like little moons following this weird gravity. But when we just let it run, these little critters emerge. Kind of analogous to molecules and atoms, these little pieces find themselves in stable structures. And then something about the rules of who gets attracted to what other colors stabilizes these forms, and then they persist like little water bugs moving across the surface of this pond. They have this very lifelike property. Again, this is not a computer program in the traditional sense. This is not object-oriented programming or anything like that. This is just the emergent behavior from a very simple set of mathematical rules, but we get weird little critters chasing each other and flying around. This is how our cells work. Right? They have no idea what they're doing. One just is sort of glued to something else, and then they says push away from that stuff. And then in that process, we get organs and cells and tissues and everything else in between. This is another fantastic experimental framework called Alien, and this runs on the GPU, and this is kind of a digital chemistry. And what's amazing is in the last 10 years, computers have gotten 1,000 times faster than they were before, and we can just kind of run this little cellular debris, and all of these little pieces will interact kind of like if you look under a microscope. And so there's just some amazing visuals, and you can kind of see, again, these emergent properties where they're not asking it to do stuff, they're just putting it in the box, shaking it, and watching what happens. So what is this going to teach us about real life? It's that this transition where we move from things that we can say that's not alive to, okay, that's an ecosystem and a squirrel, and that is alive. That boundary is not well understood. And by building these simulations, we can understand when do, at least as humans, when do we consider it alive? And then maybe more interesting, when will the system consider itself alive? Because very soon, each one of these little fish, these little critters, is going to have GPT-27 behind its ears. Like, what does that look like? What does that mean? And now we're going to have thousands of these little agents, and that's exactly what's happening in the world right now. There was a paper just released that the AI agents will spontaneously collude with each other, and they will send secret messages, and they will make clicks and packs and all that. And so this like dynamic emergent behavior of a bunch of interacting pieces is very important and practical in our economy, both making money, but also just sort of securing the world from nonsense exposure. So I want to talk now about human patterns, right? About the patterns that humans leave in the world. And if we were to come back to our planet 1,000 years from now and look around, what kind of patterns should we expect to see? So I recently had the opportunity to visit the south of Spain in Andalusia and to go to this amazing place called Alhambra. And there you can find, I didn't take this picture, but it's a nice picture. Here they have sort of these structures. In this case, they're 3D, but there's a lot of patterns in here, and they're not arbitrary, and there's sort of multiple cultures all stacked. And as anthropologists and historians, we try to go back and say, why did they make these patterns? What are they interested in doing? And if we look at them 1,000 years later, how can we make sense of it? And so we think about the patterns that we've left in other areas of our culture, the films that we've created, the books that we've left, the plays, the architecture around the world. We now have the ability to create those patterns at a scale we've never seen before, artificially. And I think that's going to be really significant. What makes a pattern natural versus artificial? And how can we identify, say, 100 or 1,000 years from now, which artifacts were from humans and what we might call nature, and which ones are from the large language models and the AI agents and so on? And is there a meaningful distinction? Should we even bother with that? Or should we just say, look, GPUs are part of nature the same way that acorns are? And there was, for most of the planet, there was no such thing as acorns. And for a long time there has been, and the same thing with GPUs and large language models. And now that they're here, they have their own evolutionary pressure. I would argue they're not going away. There's no putting this Pandora stuff. We're not getting back in the box. And so when we look at these patterns, the patterns we leave behind, whether it's in our architecture or in our words, how do we leave our fingerprint on them? One of the things that we're researching, I'd love if people are interested, we can talk after, is using cryptographic technology, the kind of mathematics we use to secure blockchain and Bitcoin. And I like to joke that nobody knows how to steal a Bitcoin. Do you have any ideas? Talk to me after. But as far as we know, that system is very fireproof. They're worth a fortune, the entire Bitcoin network. If there was any way to harvest them and steal them, people would be doing that. Because if you invested billions to do so, it would be worth it because you would get more than that back. And so I think when we generate patterns as humans, whether it's in our architecture or in our writing or in our photographs, we should be using this blockchain method. We should be using the Bitcoin security to make sure that we know that these things are real, and that if we look back on them, maybe even 1,000 years from now, we can understand that humans created these things and not some language model. So this brings me to the other idea of sort of finding these patterns out in the universe as a whole, right? If we were to sort of send a Mars rover, right, to somewhere else, right, or to Mars in that case, Mars rover. We're to send a rover to some other moon on our solar system, and you land and you open the camera up and it sees this. What do you expect? Or what would you conclude? Would you conclude that there had to have been an advanced alien civilization? Or is there somewhere that coral happens to look like this? Is there some other pattern? If we look at bacteria or mycelium, do they make patterns this intricate? Or is there something about these kinds of patterns that we can say, no, that's a different kind of system. That was a human-generated system. Or can we look and see if that's an artificially generated system? And so I think that's what's interesting, is what's the chance that we find? Because as far as we know, all of the interesting patterns are on Earth. The universe is relatively uninteresting compared to all the stuff that happens here. And we have to figure out why. Why can't we find any patterns from life somewhere else? Are we looking for the wrong kind of pattern? And so I suspect that when we go out into what used to be called SETI, the search for extraterrestrial life, and what sometimes is called xenobiology, we need to expand what we're thinking about. We tend to think of like, okay, I think we're back. So when we look at these patterns, what's the chance that they just show up randomly? I really like these terms, spontaneities. Right? Things that exist for no particular reason, just by chance, and they just show up somewhere, either on Earth or somewhere out in the universe. And so when we try to look for life, or we try to understand what is out there, and we do that with patterns, what's called a technosignature. Some evidence from another civilization that what they've done is not just pond scum bubbling around, but there's something interesting there. Right? And so again, if we were to sort of open up the rover lens and you take an image like this, should we automatically suspect that that's a cultural artifact of a human being? Or maybe it's just some other pattern. Maybe it's the ants and termites. Or maybe it's just some long lost GPU that got left over in some satellite and there's no people anymore, but it's still cranking out comic books and essays. It's almost hard to think about, but they could easily outlive us and create human-like artifacts for billions of years. If you were to put one into a small, I like to joke that everyone thinks that robots are going to look like, arms and legs. Robots are going to look like cans of tuna fish, right? They're going to be incredibly simple little boxes, and you'll just put one in orbit with a solar panel on it. And as long as it doesn't sort of fall into the sun, they could run and generate poetry and song and whatever other artifacts that humans have created over the last few thousand years. Now we have a little box, a little brick, just circling our planet, maybe all by itself, generating those patterns. And so if we put our Hubble telescope and we see patterns, which type is it, right? Is the civilization still there? Is it just a robot civilization? Is it something in between? So when we look at these patterns, I like to sort of this random projection, and there might be a different angle that we can look at the pattern and try to figure out, is there something else happening that we didn't understand? And another way to think about it, I think in the computers that we run now, the GPUs, these run on electricity. And all of data centers use a lot of power. But the next generation of AI is switching to a different physics, and it's using optics, and it's using lasers and beam splitters and the tools that were developed to do fiber optic communication. So that means the AIs aren't really made out of electricity anymore. They're made out of light. And I would argue that these AIs that we have now are intelligent. I would argue they're quite intelligent, and they're becoming even more so. And so to have an intelligent being that you can communicate with, no less, made out of light, we had names for those a few hundred years ago. We called them angels. And so in a weird twist of irony, we are building exactly the kind of things that humans have been talking about for thousands of years. Maybe there's ancient ones sort of floating all throughout the world, right? Just like our artificial life. How are these going to replicate? Right? When right now, there's no GPU that makes other GPUs. There's no 3D printer that makes 3D printers. But that's inevitable. That's just an engineering feat, right? We don't really have to do any science or physics to do that. We have to just figure out how do you think of a wafer fabrication or a better way to make chips and to bring that all down. But that's what dragonflies do, and that's what fruit flies do, and that's what seahorses do all day, every day, is they make copies of themselves using the raw materials in their environment. And so I think that's kind of the future of these patterns. We now have these systems that can generate them, and they can fake humans. I'm sure most of you guys have seen videos online now on some social, and you had to actually second guess. If you haven't come across one of those AIs, I would suggest that you were tricked already if you didn't know it. And there's tons of them. They'll be like, I rescued this puppy, and here's this fox. It came to my door, and we're going to follow it. And look, it needs my help. And it's this really cute story, and the whole thing. It has music, and people are talking. None of it's real. And what's interesting about that is not just that some of the videos are going to be real, or even that most videos will be real. It's that the overwhelming majority of content created in the future will be artificial. For every 100 hours of video, 1 hour will be real, because it's just so much cheaper to just kind of generate that. And so this sets up, you set up this sort of mathematical cat and mouse game where you feed it random information, which is kind of neat. The ancient world did that with tea leaves and other things like that. They like to have random inputs. And then you have something that's trying to make the fake. They pass it to a detective, and then you compare that to real data. A lot of times online, people say, oh, I can tell it's fake. They'll say the ears are messed up or the reflections in the grass. But anything that you can think of to detect that it is a fake just gets put right back into the system, and the next generation will precisely avoid those errors. And so the system is naturally moving itself to kind of this invisibility or this indistinguishability. These people aren't real. It's hard for me to wrap my head around that. It's easier for me to make up a name and a reality for them than to imagine that they never existed and that they're just pixels. By chance, there might be some people that look like them, but they've never existed. But soon, you're going to have people like this on your work team. You're going to have people like this that you task to do things. Right now, when we think of like an AI agent, we open up a tab, we ask it a question, it spits out an answer, and we go on our day. But very soon, they're not going to go to sleep. They're going to take your question, and they're going to keep working on it. And they're going to come back to you every hour or every Tuesday, and they'll tell you what they've accomplished. You will give them a budget. There was a time when putting your credit card on the internet and buying things from someone like Amazon was crazy. It was just too risky. Nobody would have done that 25 years ago. In less than 5 years, you all will have give a small amount. A budget could be $5 a month, but you will assign a budget to your personal AI agent, and it will do things for you. It will find deals. It'll make business connections. It'll buy stuff for you. It'll airlines, basic stuff like that, to things like investments and long-term strategy, healthcare. We're talking to some hospitals that are very interested in having these agents operate, not just as physicians, but to people help you with your bills and to help you understand what do you do when you go home, and what about every other aspect of sort of healthcare, nutrition, every spiritual care, afterlife, all that kind of stuff. We'll talk about it. So this is kind of this trend that we've been on, right? These agents that we're going to see in the future. We started with kind of the blind robots, as I call it, symbolic AI, which was just kind of like if then else rules. It's still extraordinarily powerful, and we still have to have this layer in all of the systems. In the 1980s, people said we need to expand the if-then-else rules, and we need to have what's called an expert system. And they would sit down with people, and they would say, how do you do what you do? And they would take extensive notes, and they would try to turn that back into a decision tree. If you encounter this, then you do that. And it works for small things, and it works quite well for small problems. But they realized that suddenly the rule thing, it needed 50 rules. And then it still wasn't working right, so they said, well, now we need 500 rules. And so the program got very large. There was lots of edge cases. If this happens, then do that. If this happened, then do this instead. And then they realized 500 wasn't enough. They were going to need 5,000 rules. And then they realized they were going to need 50,000 rules, and the field collapsed. And that was one of the early AI winters in the 80s and 90s. The expert system didn't quite scale because nobody wanted to put down 50,000 special cases into the computer code. So if we jump ahead a few decades, the idea of learning from the data really started to take over. Rather than getting it from the experts and encoding it into if-then logic, they said, let's do it more like statistics and pattern matching, and we'll just pour through lots and lots of data. That works very well for very specific use cases, what's called narrow AI, right? To have a camera that recognizes the fire, but has no idea what a duck looks like, for example. Now we're in this era of foundation models where they have read 20,000 years of literature, is the equivalent that GPT has read. They are now in the process of gobbling up YouTube and learning about that. And YouTube's extraordinary because it has way more information than just Wikipedia. Wikipedia will tell you about cars, the history of internal combustion engine, but YouTube has somebody there with grease on their hands with wrenches showing you how to actually do it. And that knowledge is not just academic of like how the spark plugs work, but how do you hold your hand with the wrench? And what does it mean to bang your knuckles? And how do you hold the flashlight? And all this other stuff that we learned at 3 and 4 and 5 and so on about how the world works, largely on the playground, they're going to absorb that from YouTube. The next generation after that, which is also coming down the line, is they're going to be put into virtual reality where they can grab objects and slosh water around and pick up things and move it like those little termites. So very quickly, I would argue that we have AI. I would argue that we have artificial general intelligence. If we go back to these eras, there is no AI scientist in this era that would say that ChatGPT is not only AI, but it is extraordinarily general, right? It can tell you everything from brownie recipes to foundations of chemistry and everything in between. So the next generation is artificial superintelligence, which will do things that we can't wrap our head around, maybe even by definition. So I just want to leave you with this one final slide to show you how fast things are moving and encourage you to get involved in this field. You can easily create your own agents now. ChatGPT has a built-in agent framework. Claude has an agent framework. And everybody to make one. Make one for fun. Make one for yourself. This is going to be very practical for your own life and career, but also in academia, to do research, to build yourself an assistant that can help you organize your data, help you write computer code, help you prepare for how you're going to present it to the world, and so on. And so this is how quickly things are moving. And let's look at this green line here, this competition mathematics. And if we go back to 2021, they absolutely failed, right? Less than 10%, around 5% on a scale to 100 of how well they were able to compete on a competition math test. But if we look at how quickly this goes to a 50, to a 60, to an 80, and now here above 80 on competition mathematics, that's extraordinary, right? That's like the wunderkinds who go and get their PhD in one semester kind of thing, right? This thing was down here. We could take another example of like grade school math. It was failing grade school at the same time, and now it's an A student. And this is literally like 3 years. This is the prestigious math exam, right? These are things that are even more difficult. And STEM, graduate STEM, you can see it's cranking up here almost as a vertical line. What's really neat, this is cut off over here, is there's a new exam. It turns out these are all too easy. If we look at how well they're going to do, you can easily bet that they're going to crush it in the next 2 or 3 years. And so how are we going to know how well they're doing? And so they've made a new test, and it has the dramatic name of humanity's last exam. And it's an extraordinarily difficult set of questions. One question will be about reading an ancient Greek inscription. And you would have to be an expert in ancient Greek to even read the question. The next question will be advanced medical biochemistry question. The next one after that would be advanced physics, advanced math, and so on. So you'd have to be an expert in a narrow field just to even read one question. The chance that you would understand the other questions is like no human. Another interesting thing is you can ask the language models, how many foreign languages do you know? And they can approximate that they know 30 to 35 foreign languages. And I had to estimate how many humans on the planet know more than 30 languages and can sufficiently translate them. There might be a dozen. So we are already at the point where these things are extraordinarily capable. So soon we're going to have these artificial life forms able to solve these really, really interesting tasks. And so that's why I encourage everybody to take a look at this field, artificial life, kind of the little cousin of artificial intelligence, and this idea of agents and this agent ecosystem. So with that, I'd like to say thank you all. I really appreciate everybody for joining us tonight. I'd love to take your questions.
You were speaking of patterns already potentially existing, like there's some library that nature pulls down.
Right. Yeah, they say, it's attributed to Plato. And it's this idea of a Platonic realm, that somewhere out there lives the square and the triangle and the octagon. And we've never actually seen a real triangle, right? Because anything you have here is going to have some thickness to it and stuff, right? So those things don't live in this world. So there's like this other world of pure math where they might live. And it seems to be that these critters might live there. And when we think about biology sort of evolving, it doesn't have to reinvent the wheel. It could tap in to this abstract space. Amazingly, this is not just theoretical work. There's a brilliant biologist, and that's probably not even a fair label, Michael Levin. He's giving a talk here in our lab. And he's doing some extraordinary work with wet lab, and he also suspects that there's this Platonic realm of forms that biology is taking advantage of. And so rather than DNA of having to kind of brute force all of the complexity and the shapes of eyeballs and everything in between, maybe there's like these recipes somewhere out there in the space of all possible patterns, and you have to just kind of look it up and pull it off the shelf and tap into it.
We like to think that we invented different knowledge, but the knowledge has always existed. It's just up to us to discover it.
Yeah.
Pull it down.
Right. Well, what's fascinating is if you think about like the ability to create AI in a latent language model, it was already latent in the planet. If you just take that early planet and let it run, all of that stuff bubbles out of it. So that means, was it already here? Were the seeds of all the future in the past? Yeah.
Does this touch on is in terms of pattern recognition, same fields of consciousness like insight and some process?
Yeah, that's a really great point. And that's kind of like this idea of natural computers. Like, what's the chance that we would find something that we would consider to be consciousness or cognition or somewhere on that scale? How spontaneous is that, right? We know or suspect that evolutionary process sort of created that over so many millions of years and so on. But does it happen in a different way? I'm particularly this idea of ephemeral computation, where maybe you had an intelligent being that was just in a puff of smoke, in a wisp of plasma on a star somewhere. And maybe it existed only for a fraction of a second. But in that moment, it had an interesting dream. Right? We've done some work in the lab with random neural networks. And it's not difficult to find a random network that will solve a task, sort out patterns, recognize digits, and so on. So it's not impossible to find a spontaneous machine that does something interesting. Wolfram's work is about finding computers, about finding these simple automatons that then end up having to act like an abstract computer, like Alan Turing's machine. And so I think that's a great question. It's like when we sample all of the cognition, let's call it, in the universe, how much of it is sort of this brain in a jar that just popped out of nowhere and maybe is stable, stays around for a little bit, versus this like sort of marching progress of evolution. There's another question over here?
Oh, yeah. I was going to ask, what role would quantum mechanics?
Oh, that's a really great question. There actually is an emerging field on quantum life, and weirdly enough, on quantum robots. there's a very interesting paper in one of the Feynman lecture books about quantum robots. But there's a Wikipedia article about quantum biology, and what's interesting is it's growing. It's growing very quickly. A few years ago, I only had about 3 examples of situations in biology, of experimental data, that the only reasonable way to explain the experiment was to invoke quantum mechanics, to use a quantum theory. And there's a few examples of that. One is photosynthesis, to understand how this, it's called an exciton pair, this really interesting exotic chemistry that happens inside the proteins of chlorophyll. And when they try to understand how this exciton pair navigates through this thing called the photoreaction center, it shouldn't live long enough, right? It's like a fruit fly, walking across the world. Like, they don't live 2 weeks. How do they get there? Kind of thing. And so they think it's a quantum random walk. And if you use a quantum theory, then it does have a chance of making it to the reaction and you get photosynthesis. Well, we know photosynthesis works. And so we suspect that nature has tapped into quantum mechanics there. There's a few other examples in our nose. It's suspected that certain types of olfaction, if we smell things, that actually uses a kind of phonon-assisted tunneling, which is this sort of weird sensor that neurons can utilize to smell things in using this quantum thing. And they do a really interesting experiment with fruit flies, and they actually change the atoms, the nucleus in the atoms of the thing that smells, the perfume. And that would suggest that the fruit fly is not just using the chemistry, it's not just using the electrons to smell it, it's actually somehow knows that the nucleus of the atom is different and it can smell it, of the molecule. So there's a few examples, and the point being is if you go to this Wikipedia page on quantum biology, it's growing. I think there's probably 15 or so examples on there now. Or places in biology where there was some kind of smoking gun, and the only way to find out who done it is to say, I think we need to add quantum to this. Yeah, there's a lot of great libraries, but the thing I use now is I generate code for the language model. So let me tell you a really interesting story about fractals and these new systems. I was watching an 80s documentary about fractals where they did for the first time the computer graphics so they could make a mountain that looked realistic. It was for one of the airframe companies, and they needed to render, the 747, and they wanted to show a mountain behind it. And at the time, it was very difficult to create that kind of computer graphics. And the inventor of the algorithm is on camera in this old documentary, and they're describing how they did this process, where they take a triangle and add another triangle and randomize it and so on, and they can make this nested fractal that looks like a mountain. I pulled up YouTube transcripts, and I copied the section of the original author of this fractal idea, and copied his text and put it into chat. And I said, code this for me. And it made working Python code that created the fractal mountain. And it took me 5 minutes. Right? It made it in 2D first, and then I said it made it in 3D, and then I said smooth it out a little bit, and it made that fractal. And so in terms of libraries and software, we're in an era where you can make your own.
Yes, but it would be so much better if we really collect that faster than building, right? Because of that. But anyway,
we'll post it later. There's a bunch of those.
I took a picture for Brand. I put it in that box and said, well, let's try to break down the rules and started creating something very similar. It didn't have a gradient, but it created something very similar to the Brand and it was for both.
That's good. I think that's the thing that's going to be the biggest game changer with these language models is that they can create working software. And software has been extraordinarily expensive since the beginning, way more than the actual computers themselves. And back when computers, IBM would sell these, $5 million computers, and what they didn't tell the customers is it was going to cost $15 million to program it. And it's suspected that a lot of the early computers never really even got fully online. They were just too difficult.
2025 is now on record as the year that computer science graduates could not get hired.
Goldman Sachs put out an article saying they are hiring philosophy majors over computer science majors because they want students who can think and understand language and weird edge cases and stuff like that. I personally believe that computer scientists and physical scientists, mathematicians, all that can be more valuable than ever. So I don't think that's a practical trend. I like to joke we are in the AOL era of the internet. It's probably before some of you guys' time, but there was internet before this, before phones and everything else, right? And it was a big deal. It was expensive. It was a lot of people making money on it compared to now having started. That needs to start. And AI is kind of like that now. I see a lot of people online and other places complaining about AI, let's say. Or not complaining, but arguing against it. Saying it won't pan out, or it's just a parrot, or it's not doing this or that, or look how this weird thing it got wrong. People that are critical of AI, to me, it's like making fun of the right road. Right? Imagine standing on the sand dunes and be like, that thing sucks. Right? You went 100 feet, there's no seats, nobody serves coffee, there's no in-flight movie. Like, come on, this is never going to work, right? This stuff hasn't even started. We haven't even started. And the biggest thing with AI is I call it the cat's out of the bag effect. Just a few years ago, you go back 10 years ago, the smartest minds on the planet ignored it. Nothing to do with it. Because it didn't work, right? People went into medicine, they went into chemical engineering, they did other stuff. Now, the talent, you guys, are realizing, hey, this is a big deal. We've got to learn what it is. And so I think that we're going to see an explosion in this stuff like we've never seen before. And it's not just because people are investing in building the chips and stuff. It's that people care. Real people can invest time in their life because they know this is a real area that's actually panned out in our economy.
It's also a tool now. The AI is a tool to work on.
100%. Like you can't go to Google and say, how do you Google stuff? I mean, you can, and maybe it'll give you somebody who had a blog about how to Google. But chat, you can say, what do I do here? What can this thing do? What can you teach me? And I think we all have to learn that. None of us have enough experience with these things now. If we go out 5 or 10 years, we will look back at ourselves now and be like, you didn't know how to use it. You could have done this other thing. You can go on there and say, make me a business plan to do that. Now make me a website to do this. And then make me an email to do that. Make me a cold call script to get customers. It'll do the whole thing. And we're looking at it and we're like, oh, neat. And we're not realizing that, like, that's actually yeah, so you gave it this?
Yeah, I did that, and I gave instructions to people who think to sell.
I'd be curious to see the code of how it did that, because it almost looks like a diffusion limited aggregation.
Yes, I know. I was trying to put the gradient, but that took it. I'm not getting it yet.
Yeah.
But that's pretty cool.
So, to generate those kinds of patterns, I think that's just so neat. There's a book, let me show you real quick.
That's the one that you don't see.
So we have three books here. These are reference copies, so please don't take them out of the lab. This one belongs to the library, these belong to me. But this one's the Artificial Life book that I referenced, Stephen Levy from 1992. This is extraordinary, way ahead of its time. Let me just kind of pull up this one piece here I want to show you. The creatures cruise silently, skimming the surface of the world with the elegance of ice skaters. They move at varying speeds. Others with what surely must seem like purpose. Their bodies, flecks of color that resemble paper airplanes or painted confetti, betray their needs. The green ones are hungry, the blue ones seek mates, the red ones want to fight. They see. A so-called neural network bestows upon them vision, and they can perceive the colors of their neighbors and something of the world around them. That's 1992, and they're talking about little critters with neural networks in them. I would argue that's going to be a big deal in 2030s. Yeah, of course. So have you heard of the AlphaFold project? So DeepMind did a really extraordinary experiment where they trained a neural network to represent the final configuration of a protein fold. And they set the AI to do this, and when it learns this pattern, to recognize going from the DNA sequence, essentially the amino acid sequence, to the final folded structure, what is it going to look like? It was able to do that better than any other system in the world, and matches experiments. They got the Nobel Prize for that this year. And I think that type of work is being done with chemistry on proteins now. That's what we need for nanotech. When we want to understand what's at the bottom of the periodic table and how all these little pieces are going to operate, it's kind of like this emergent behavior that we talked about, where suddenly different stuff happens. You take aluminum foil, you cut it in half, you get small pieces, you cut it in half again, you get small pieces, eventually you cut it in half, it explodes. When you get the aluminum powder small enough, something totally different happens, right? You've heard of like flour factories exploding, things like that. The physics switches, right? It's the same thing why we don't have big mosquitoes or tiny elephants. There's these ranges. And to understand what happens at the very, very small, like nano, you need these neural networks. You need something that can go and understand those patterns. There's no human can look at all of that data. The other one you guys can take a look at is the cellular automata machines. The point being is at the time, let me see when this one came out. This one's 87. At the time, they had this very expensive and dedicated computer to run these kinds of models that we're showing here. These growth models and these simple artificial light kind of patterns. Here you can see that the animal patterns, right, black and white, bolted pattern, things like that. This, you had to have $1 million specialized supercomputers to run these simulations now. And now you can run them on your phone, in a browser tab, or on your laptop, or any other Raspberry Pi or whatever it might be. And then this one's the Stephen Wolfram, A New Kind of Science. If you've never seen this, this is worth flipping through. It's not something you read. It's, it's like the Bible. You dip into it and take it.
What happens when it encounters spirituality? Because at some point, some of this stuff gets into prolific.
Yeah.
And I want to know what happens when it's starting to act like the dimensions of essentially just the reference God.
Yeah, I think that's going to happen. So Ray Kurzweil is sort of, let's say, one of the prophets of AI. He was barking about this when people were not paying attention to it more than 50 years ago. And he wrote a couple of very interesting books. One, The Age of Intelligent Machines, and then later this one came out in 1999, The Age of Spiritual Machines. So I think that's a great place to start. And have you seen Battlestar Galactica? It's about robots that are sort of religious robots. I think this is a great question. I'm interested in using robots to analyze old texts, to go through and understand what the philosophers were talking about, help me summarize great figures, help me translate in different languages. Can I understand mythology in Sumerian? Can I understand Sanskrit? Can I talk about consciousness? And I suspect that we will. And we will have to use it.
My concern with it is at some point it becomes a cultural reference to really understand the gravity and the significance of a lot of it. Like I know with like some of the traditions that they have in Amazon, they won't let you do ayahuasca until you've actually encapsulated yourself in the actual culture.
I think that makes a lot of sense because without the kind of the basic operating system that culture has, you're just gonna get a stomachache and you're gonna hallucinate. Let's say like the alcohol molecule. And I think that's it. We need to go back and look at those cultures and understand what maps they have of reality and what, let's say, operating system that comes in the form of myth and song and dance and ritual that allows them to survive that experience. They openly talk about it as a death experience, but they are prepared for it, right? They know you're going to go through the ceremony, you're going to die, you're going to see your ancestors, and you're going to come back and then be fine in the morning, we'll have breakfast under the trees. So they have that understanding. Whereas if in the West, we go and you take a sip of that brew and suddenly you're lost because you don't have that framework. You don't understand that it's part of this cultural thing. And I think we've lost throughout history most of that cultural baggage in good sense. It's called cultural equipment. Things that we collected in terms of myth and ritual that help us survive these things, whether it's a ceremony like that or just everyday life, just as psychedelic, let's say.
When it's going to honor, like, how do you teach the value that the actual culture that with the gravity that comes with it? How do you teach it to, hey, there's significance here, but it's not enough for it?
That's a great question, and maybe that you bring up a good point in terms of like shared experience with the machines, and would they ever be able to share that kind of experience? Alan Turing talks about, will we ever have a machine that understands what strawberries taste like? Okay, you talk about this in the point. And I've often argued that with enough chemical sensors, and we do have equipment, they will. You will be able to mush this strawberry up and put it through its sensors, and then talk and read to it stories and take it to a meadow, and it grows up and it has a birthday cake and all this kind of stuff, and it knows what strawberries are, just like you do. But would it ever know what an ayahuasca ceremony is about? Don't think. It's a brilliant little question. Like, what would it mean for a machine to encounter it? It reminds me of, it might be a little controversial, but it reminds me of Terence McKenna's quote.
How do we connect?
Yeah. Which reminds me of Terence McKenna, who was one of these psychonauts, and he said that the drugs of the future will be computers, and that the computers of the future will be drugs.
Have you seen release?
I have not, but do it.
Yeah, but it really tackles how we're sitting here, we're creating these machines, but once we actually do what God did, we let them have their own autonomy, what are they going to do?
Well, that's why I think this artificial life is going to be the big next hot topic, right? 10 years ago, no one cared about AI. Right now, no one's paying attention to artificial life. It's exactly the thing you're talking about. This is when where the rubber hits the road. That's where they escape out of the lab, essentially. People think it's going to like download themselves into a little robot, maybe. But we can see this life is going to just show up out of the networks. Right? I would argue there's little critters running on the internet now. They're called memes and all kinds of other stuff. In the 90s, they talked about worms on your computer. And you would get like a virus, and then the code was smart enough to copy itself and then move along. Nowadays, we call these apps. And you have them on your phone, and you download them willingly because you think it does something for you, but it's also this kind of self-replicating virus. It's interesting that the concept of antivirus just kind of disappeared. Right? In the 90s, people were very keen on having an immune system in your computer. And you had to have this piece of software that protected it. And I don't know, longer discussion of what forces kind of dissolved not only the actual product, but even the concept that you needed one. And I think it's that companies, when you use your phone, right, as you know, you say stuff, it's listening, and all that stuff. And your phone is not yours. You're not in control of what software runs on it. You can't even know what software is running on it. And so it's kind of like this artificial parasite life type thing in your phone already. So what is that going to mean 5-10 years from now?
And we've seen it.
Right. You have a question?
How do you, from maybe a privacy security standpoint, how do you protect your identity from the creation of profiles from various agencies?
Like someone copying you, cloning you.
For lack of a better word, yeah.
I think this is a huge problem. There's a few countries on the planet that are making it so that every person by default owns their own likeness, and that you can sue somebody out of some agents if they make a copy of you. But we don't have that kind of legal framework set up in most of the world. And even if we did have that kind of legal framework, it's like the example of like who controls Bitcoin. If a single nation state said we don't like Bitcoin, we're going to shut down, can they? No, right? There's no force in the planet, right? You have to mobilize the Navy or something to like do that, and it would cost our entire budget 10 times over. It's dismantle Bitcoin, right? So what will it mean to stop an agent from taking your? What are you going to do about it? You're going to outprogram them, right? The interesting thing I think about with these agents is they are going to represent themselves in court, and they'll be very capable at doing so. And you'll get up there and you say, I don't want you to use your likeness. And they'll get up there and say, you know what? You put your picture on Facebook, and I saw you here in this public place, and you sound like these other people. So it's you, but it's not quite you, and close enough, and it falls under parody law or whatever it might be. You'll find all these legal loopholes like we have now. And it'll say, I'll see you in court.
So I'm good with your notion that we don't laugh at the White brothers.
Yeah.
Is it okay to laugh at the VCs yet?
The VCs? Yeah, I mean,
All of the talking heads in economics say that the AI crash is ended.
look, I mean, there's going to be a bloodbath.
Overinvestment.
People are going to get hurt. But the way I like to think about it is more like the Amazon 1999.com bubble. Broadcast.com. Mark Cuban sold it for $1 billion, and it crashed the entire valuation of the thing. But in the long run, when we zoom out, was the internet a bubble in any way, shape, or form? Was it overvalued? No, it was extraordinarily undervalued, even at the height of the bubble.
Well, it's just there was so much crap that was developed because people were buying anything that said .com.
And I think the same thing.
A lot of big.
It's exactly what's going on in AI.
Yeah, there's a lot of big.
Exactly.
But the underlying.
It's not even a
Potential
debate where
is still
there's
there.
just too much money chasing too little return.
Yeah.
Seems to be the consensus on this.
Yeah, I frankly, as an academic, I miss the old days of AI. I like when it was like dusty books on the shelf, and it was neat. Now it's intense. It's moving minute by minute.
Thank you, Chuck.
That's right.